Compression does not always mean crushing. While a short block might safely carry a load until it reaches its yield stress, the behavior of a long, slender column is dictated by stability, not just material strength. It can suddenly bow sideways and lose all load-carrying capacity at a much lower stress. This dangerous instability is known as buckling. In this lesson, we will derive Euler's critical load, examine the possible mode shapes, explain why the first mode always governs, and compare yielding with buckling. We will wrap up by looking at a real-world steel stress versus slenderness graph and practical design code limit. What exactly triggers this mechanical instability? Imagine a compressive force P acting on a column that has deflected slightly sideways by a distance y. That force now has a lever arm, creating a bending moment equal to P times y. This new bending moment pushes the column farther sideways, increasing the deflection, which in turn creates even more moment below a certain critical load. The material's elastic stiffness is strong enough to push the column back towards the center. But at the critical load, a threshold is crossed. Both the straight shape and a slightly bent shape can satisfy equilibrium. Push it any further, and the straight shape becomes mathematically unstable. In reality, tiny imperfections, vibrations, or micro defects ensure that the column will immediately choose the buckled shape. So why not just divide the load by the cross-sectional area and ensure that it is below the yield stress? Because P over A measures stress in the material, not the geometric stability of the structure. A short column usually yields near the yield load P sub y equals A times F sub y, but a slender column can violently buckle while its average stress is still far below the yield strength. F sub y yield stress is not ignored. It governs short columns and is used in modern inelastic design curves, but it cannot predict a length-dependent instability. For that, we need Euler's formula, which accounts for elastic modulus E, second moment of area I, effective length, and boundary conditions, the true parameters controlling lateral stiffness. Let us now look at the classical derivation. We start with an ideal prismatic column pinned at both ends with a total length L. The load P passes perfectly through the centroid. We assume that the material is linear elastic, all deflections and slopes remain very small, shear deformation is negligible, and the flexural rigidity EI remains constant. These assumptions are deliberate. They strip away real-world complexity to set up a perfect eigenvalue problem. Let x run along the column and let y of x represent the small lateral deflection. If we cut the column at any point, the axial load P acts through a lever arm y, producing an internal bending moment. Using standard small deflection beam theory, the internal moment equals flexural rigidity times curvature. Therefore, M equals EI times Y double prime. Equilibrium of the deflected column section also tells us that M equals minus P times Y. Combining the two relations gives EI times Y double prime plus P times Y equals 0. Dividing by EI and defining K squared as P over EI gives the classic second-order differential equation. Y double prime plus K squared Y equals 0. Notice the mathematical beauty here. The unknown is not only the deflected shape. The load P itself must take specific discrete values before a non-zero shape can satisfy the conditions at both ends of the column. The general solution to this differential equation is y equals C1 sine kx plus C2 cosine kx. Now we apply the boundary conditions. The bottom pin requires y at 0 to equal 0, which forces C2 to be 0. The top pin requires y at L to equal 0. If C1 is also 0, the column has not buckled at all. So for a physical buckled shape to exist, sin KL must equal 0. This means KL must be a multiple of pi. KL equals n pi, where n is an integer, 1, 2, 3, and so on. Substituting K squared equals P over E, I gives the critical buckling loads, or eigenvalues. P sub n equals n squared pi squared EI over L squared. The corresponding buckled shape is proportional to sine of n pi x over L. This mathematics reveals several possible buckling modes. Mode 1, with n equal to 1, forms a single half wave and requires the lowest critical load. Mode 2 forms an S shape with two half waves but requires 4 times that load. Mode 3 requires 9 times the load. So why do engineers normally use n equal to 1? Because as a real load rises from 0, it reaches the smallest eigenvalue first. At that instant, The straight configuration loses stability. The column cannot remain calmly straight while we continue to 4 times the load to trigger mode 2. Higher modes become important only when intermediate bracing suppresses the first mode, or in specialized modal and dynamic buckling studies. In the real world, columns are not always pinned at both ends. To account for the end restraints, we replace the actual length L with the effective length KL. A cantilever has K equal to 2, so it buckles at only 1/4 of the pin-ended load. A pinned column is our baseline with K equal to 1. A fixed pinned column has K approximately equal to 0.7, making it about twice as strong. A fixed column has K equal to 0.5, allowing roughly 4 times the pin-ended load. The universal elastic buckling result is P critical equals π²EI divided by KL all squared. Because effective length is squared in the denominator, end restraint has a major effect on column capacity. If we divide the critical load by the cross-sectional area, we obtain critical stress. Introduce the radius of gyration, r equals the square root of I over a, and define slenderness ratio lambda as KL over r. Euler critical stress then becomes sigma critical equals π² divided by lambda squared. The graph falls steeply as an inverse square. For typical structural steel, take elastic modulus E as 200 gigapascals and yield stress F sub y as 250 megapascals. The Euler curve intersects the material yield line at a slenderness of about 89. To the left of this intersection, Euler theory predicts a stress higher than yield and is not valid, yielding an inelastic buckling governed. To the right, the column is slender and elastic buckling becomes the dominant failure mechanism. Do not confuse this theoretical transition point with a practical engineering limit. Maximum slenderness is controlled by the governing structural design code. Under IS 800-2007, a member carrying compression from dead and imposed loads has a maximum effective slenderness of 180. If compression is caused only by wind or earthquake combinations, the stated limit may increase to 250. Meanwhile, AIC 360-2022 recommends that L sub C over R should not exceed 200 for compression members. On the graph, ideal Euler stress is only about 61 megapascals at a slenderness of 180 and about 49 megapascals at 200. The practical lesson is simple. Always design to the applicable code. Let us run a quick example. Consider a steel column with an area of 4,000 square millimeters, a minimum radius of gyration of 40 millimeters, and a pin-ended length of 4,000 millimeters. Take E as 200,000 megapascals and yield stress F sub y as 250 megapascals. The slenderness lambda is exactly 100. The second moment of area, I equals AR squared, is 6.4 million millimeters to the fourth. Substitution into Euler's formula gives a critical load of about 790 kilonewtons. The yield or squash load A times F sub y is 1000 kilonewtons. Therefore, elastic instability governs in the ideal model. Real design strength is lower because initial crookedness, residual stress, load eccentricity, connection flexibility, local buckling, and safety factors all reduce the capacity. Let us summarize the key takeaways. First, buckling is a stability failure, not simply material crushing. Always use the least flexural rigidity and the correct effective length. Second, Euler load varies directly with E and I and inversely with the square of the length. The first eigenmode governs because it has the smallest critical load and is reached first. Yield stress controls the strength of short and intermediate columns, but by itself, it is blind to slender column instability. Finally, Euler theory is a beautiful theoretical benchmark, but it is not a complete design rule. Real steel columns must be checked using the governing code's column curves, slenderness limits, built-in imperfections, and the relevant flexural, torsional, and local buckling modes.